It's about time to start here. Welcome everyone. My name is Sidney Chan. I'm a product marketing manager over at Dialog Semiconductor. Some of you may have noticed we have a new company name and logo. We were formerly Silego Technology, but due to the recent acquisition, we're now under Dialog Semiconductor, and I think it's a great thing. We're kind of pulling together our configurable mixed signal ICs together with the expertise that Dialog has with regards to power management, with regards to Bluetooth connectivity, and also very fast charging for your tablets and cell phones. So with that, let's go ahead and get started. The topic of today's webinar is implementing low power IoT devices with hybrid energy storage systems. And this is actually the first of, or the third of three webinars we've already had as part of a series. And as we're getting started here, let me first thank a few authors on who wrote some of the app notes on which this presentation is based. First and foremost, it's Dr. Ramaswamy, who wrote a boost converter design for energy harvesting applications. Just today, we posted the latest articles. It was an addendum to that to add like a simple lithium-ion charger, and also a more deep dive on lithium-ion charging called compact rapid charger for lithium-ion cells. I've had the pleasure of working with Dr. Ramaswamy on a number of application notes, and he's done a fantastic job for us. Also, we're basing some of our circuitry on an app note written by Yuhan Sun. She's our application engineer here in the Silicon Valley in California. It's the speed regulating PWM fan controller, fan motor controller. And finally, a third application note by Shimpe, who's a field application engineer in our Japan office. So thank you him for our LED dimmer with analog regulation app note. You can find all of the app notes online. Just navigate your way to silego.com and go to our supercapacitor landing page, which deals a lot with energy harvesting material. Or you could just go to our application note website, which you can easily find. In any case, I would like to say that, in case you're not familiar with Dialog Semiconductor's application note for configurable mixed signal ICs, not only do you get like application notes, with a lot of detail in them, but you also get an accompanying design file for each one of those. So you can easily just download it onto your GreenPAK designer software and start playing around with it, simulating with it, and even programming a part with it if you have one of our evaluation kits, right? So it's really unique in that regard. Okay, jumping into it. So the purpose of kind of looking at this topic is really how to address the IoT power challenges with the parts that you have on hand in the market today. And the challenge comes from the fact that IoT devices continually consume power, and ideally they can operate untethered from your traditional power sources, meaning it's not necessarily wired or something like that. It could just operate on its own in remote location, for example. So designers definitely don't want to limit the device functionality of their parts just based on the available power that's there. And that's for obvious reasons. In fact, there's a trend to move towards more fully featured products, if anything. So there's more features added, more bells and whistles, and at the same time, users don't want like a bulky device, right? And they don't want to have to deal with like frequent battery recharging, for example. Just think of like smartwatches or your own smartphones. You don't want to always constantly be charging it, for example, or even replacing it, So that's kind of the challenge with IoT devices. And one potential solution that we're going to explore further in today's webinar is adopting a more of a hybrid energy storage approach, using both a battery, like a secondary battery that's rechargeable, as well as the energy harvesting source to do that. And by doing this, you're really taking the best of both worlds, because on the one hand, you're offering the reliability and familiarity of lithium-ion battery, for example, you're adding that in conjunction with the sustainability of an energy harvester. So you're constantly getting new energy without having to plug in some main power source. So we're going to show you a couple schemes on how to do that. And I thought that for the purpose of this webinar, it would be useful to kind of do a recap of our prior webinars that were given in this series. They were given by John McDonald, our VP of Marketing, and they really focus on powering IoT with supercapacitor-based energy harvesting systems. Obviously, you can use like traditional battery sources or energy storage sources, but supercapacitors have come a really long way, and it's pretty exciting to see the advances happening in that regard. So our very first webinar was looking at supercapacitors in detail and really understanding their characteristics and how you would design around a supercapacitor as the primary energy storage mechanism. So we looked at very basic things like active cell balancing of those supercaps, charging and discharging of them, monitoring the temperature to make sure that it's not like aging prematurely, or detecting if there's any electrolyte dry up, which is the liquid inside of the supercaps. We looked at how you might want to maintain a fixed output voltage in the simplest case to provide a very usable and practical output voltage source. And of course, some protection things like short circuit protection, overcharging, and reverse voltage. And using that knowledge and building on that, next we looked at energy harvesting using supercaps. So the primary theme in that particular webinar, the last one, was that we try to accomplish DC to DC conversion, because as many of you may know, and if you don't, you can refer back to the prior material, supercapacitor charges and discharges in a relatively linear profile. And in that regard, if your output requires a certain load with, certain voltage tolerances, well, you really need to provide or have some kind of power conversion happening there. So we did a deep dive on implementing circuitry using our GreenPAK technology to actually do PWM generation. And we also implemented features such as duty cycle bounding, whether it's overflow or underflow. We looked at low energy detection, so you can kind of put the entire system in a low power state or start shutting stuff down, for example. We gave a simple provision for battery support, like if you wanted that to complement your supercapacitor, and we also added overvoltage protection. Now, for this webinar, we're building on both of the prior webinar series and, delving into a hybrid energy storage system, as I mentioned. And it's really in two parts. The first part, I'm going to talk about if you make certain simplifying assumptions, you can really simplify your design and implement, just add very little circuitry to the existing circuit that we developed last time. And on the second hand, if you can't make those simplifying assumptions, how do you build a more general purpose lithium-ion battery charger to meet your particular application needs? And to do all this, it was done all, of course, in the context of an actual application example. So we had looked at electronic door energy harvesting application, where we would capture the energy from the door actually opening, so harvesting that mechanical energy from that, storing that momentary burst of energy into a supercap, and then using that to power an electronic door lock. Here it was modeled as a 5-volt load with very bursty type of load profile. But drawing all that together was a CMIC at the heart of it, a configurable mixed signal IC provided by a Dialog semiconductor. And that's depicted here in the center of the slide. And the advantages of that are, a number of things. Number one, you can integrate other circuit functions. You can also incorporate very context-specific controls that are kind of unique to your particular application. And the third thing is that it's just small and customizable. So, I mean, these are kind of just winning features that would make it attractive for you to use in the heart of your system. And for this webinar, we're adding, of course, the lithium-ion battery for the reasons that it's relatively low cost, it's readily available, and it can provide you with a very long-term energy storage to complement the supercapacitor. Okay. And just to touch a little bit about the CMIC itself. So our tagline, well, the main advantage for CMICs is, as I mentioned, faster designs. It's faster, it's smaller, it's lower power. And literally, in terms of the design cycle, I mean, you could be designing in a couple of minutes, just laying down the blocks using our GreenPAK designer software. You can start prototyping in hours, because what you can do with our evaluation kit is download that particular design, which requires no coding, into an actual GreenPAK device right at your desk. And then literally, if it looks good to you, you can ramp up production in as little as a few days. So for very high volume applications, I mean, we typically quote lead times of like 4 to 6 weeks. That's much shorter than a lot of the suppliers out there today who are quoting, I hear, like probably like 4 to 6 months, if not more, for procuring parts. So that's a winning advantage, I think, when you're looking at this particular technology. By the way, if anyone has any questions, feel free to ask it. Otherwise, we should have time at the end of our presentation to field any questions that you may have. All right, so jumping into it, our one useful thing when you're looking at lithium-ion batteries is maybe to just compare it with a more traditional lead-acid battery. Some of you may be familiar with this technology, but in a sense, there's 3 primary charging phases. The initial one being what some people would call the bulk charging phase. And that's where it's usually a constant current. It doesn't have to be, but usually, more often than not, it is. And that would be followed by an absorb charging phase, where the voltage is kept constant while the current levels off here, as you can see. Let me turn on my laser pointer so you can see here. But yeah, you can see here at the bottom, as you know, you hold the constant voltage during the absorb phase, the charging current kind of levels off. And then finally, there's a final float charge stage where the battery is kind of held to a slightly lowered voltage and just kept there. And the key thing to note here is that it's important to complete all 3 of these phases in order to optimize your battery performance and make sure that you maintain the longevity of the battery itself. When you look at a lithium-ion battery, in contrast, it's a little bit different. So let me walk you through this one. The key differences from lead-acid battery, the first thing you might notice is that at the end, there is no float phase. So the charging current must basically drop to 0 once it's completed, once the absorption phase is completed. And you would have a charge current of say less than 0.1 C, usually see something like 0.05 C. Another thing is that in the beginning, if the lithium-ion battery is deeply discharged, it's very important to trickle charge it and not kind of give it a burst of current or anything like that. So that would help prep it for the bulk phase, which you can see depicted here. And a couple of observations that we want to take advantage of in the first part of this webinar is that if the charging is actually stopped before the absorption phase is completed here, the battery life is, well, it doesn't adversely affect the battery. In fact, it actually improves the battery life if you do that. So we can take advantage of that. The fourth point here is that slow charging is actually good for the battery. And to illustrate that, I've taken just a snippet from the batteryuniversity.com here, where we've taken these figures from. And just to illustrate the point, so if you're charging, for example, at 0.7 C, that results in a capacity of about like 50 to 70% when the 4.1 volt of a lithium-ion battery is reached during charging. Whereas if you charge at less than 0.2 C, which is maybe like a third of that, that can actually result in a full battery state as soon as the voltage reaches that same 4.1 volt. So the takeaway is that it's actually advantageous when you're doing very slow charging. And if that's okay for your application, it's fantastic. So moving on, some of the simplifying assumptions that we can make for this first design is that number one, if we assume that the lithium-ion battery won't ever be overly discharged, we can really simplify the circuit. Or if it's not an assumption you can make, maybe you just design for it, all right? But in essence, we can get rid of the trickle charge phase at the beginning of the design. The second thing is that because for energy harvesting applications, usually the loads are actually not very power hungry, or at least the ones that you may be dealing with in your particular electronic design. So for you as a system designer, it actually may be more important to have extended battery life versus having to charge the battery to the full 100% all the time. So we can actually exploit the third property, which is that we can stop the charging before the absorption phase is fully completed. And by doing so, we actually lengthen the longevity of the battery. And the third thing is that because the charging currents are relatively low, we can actually just get rid of the absorption phase altogether and basically slowly charge the circuit. So the bottom line here is that, as you can see here, we're left with only the bulk phase to contend with. And that really helps to simplify our circuit. And what that circuit looks like is as follows. This circuit, the primary parts here are actually taken from the prior webinar, or prior app note design, the app note 1202. But in that design, let me just do a recap for those who may not have seen it yet. But in that particular design, we used one of our mainstream GreenPAK products, the SLG 46533. And we did a number of things. Primarily, the biggest thing we did was implement a boost converter. So you'll notice that we have an inductor here, a diode, and like a switching FET here. And it's just a single stage boost converter design. And the GreenPAK essentially provides the necessary control signals and the PWM pulse control signals to drive this circuitry. So that was the primary thing. Not only to generate the PWM signals, but we're doing such things as duty cycle bounding for both overflow or underflow. We did things like low energy detection, and we had some provisions for second battery support. And what's happening here is that by implementing that same circuit and only adding two things highlighted here. First, we added a GreenFET product. It's the SLG 59M1639. And we added one resistor. And by doing that, and keeping in mind the simplifying assumptions we made, we were able to implement lithium-ion charging. So let me walk you through that and what needed to happen for that to be designed. So in essence, the Q2B here is connected to the terminal of the lithium-ion battery. And when the FET is on, in essence, the lithium-ion battery is charging from the output of the system. And it only charges whenever the supercap depicted in the center here of the circuit, when it only charges the lithium-ion battery, number one, when the supercap is already fully charged, and number two, the battery is not. So it's a very simple scheme here. What you'll notice is that with R1, we're actually recycling the resistor we had before to bleed away any excess energy in case both the supercap as well as the lithium-ion battery that we're adding is already full. And R4 here is basically chosen so that the overall load is small enough so as not to cause any excess output ripple. And usually we recommend to keep the charging current to less than or equal to 0.1 C. And following this, we're going to look at what's actually inside of that GreenPAK design. So what's inside of this green box here? This is what it looks like, the additional circuitry that we added. So all we added was simply this analog comparator number one to monitor the battery voltage. In the previous design, we only had one analog comparator to monitor the supercapacitor input. And the analog comparator that's monitoring the battery is configured with 200 millivolts of hysteresis. It has a gain of 0.25. So when you look at everything, basically the battery is going to be determined as full whenever that threshold reaches like 4 volts. And we're going to say that it needs charging whenever it drops below 3.2 volts. The supercap voltage monitor is monitored by the analog comparator number 0. The NAND gate controls that bleed resistor that I mentioned earlier. And lookup table number 14 is responsible for turning on and off that Q2B that we added. So this is in essence the design, and you can see just how simple it is to implement. So hopefully that gives a lot of you out there a lot of confidence in adopting this design for your particular application if you can make those some of those assumptions. And if not, you can basically take the same design and modify it for your own use. So these are all like open source type designs. All right, so mind if I take a swig of water here? So for the second part of the webinar, what happens if you can't make those simplifying assumptions? So in this case, it was number 3 and number 4 here. So what we don't want to do is actually stop the charging before the absorption phase is completed. So we'll keep it very general, a general charging profile. And the second thing is we actually don't want slow charging. We actually want it to charge at a pretty nominal rate that's healthy for the battery. So what would that particular design look like? Well, let's first talk about what would be the broad design strategy to make a general or custom lithium-ion charger. So the first thing is that we would, number one, need to deal with two voltage thresholds. The first one being the deeply discharged threshold in case the battery was depleted when the charging started. The second thing is you would need to detect the voltage threshold for when you want to do the absorb stages. And the third thing you would need to detect is actually the current threshold, just to know when the current during the absorb phase has dropped below a certain predetermined charge termination threshold, right? So with these three things in mind, how would you accomplish it? You can definitely go out and buy a general lithium-ion charger, but what if you wanted to tweak it for your particular energy harvesting application? That's really where a GreenPAK configurable mixed signal IC comes in. We have a couple of choices here. We can choose a GreenPAK device with at least 3 analog comparators to measure those 3 things that I just mentioned. Configure it for both voltage and current threshold detection. A good part to start off with would be our SLG 46533, which is one of our mainstream GreenPAK parts, in conjunction with an external GreenFET or load switch of your choice. But what we're actually going to explore in this particular webinar is choosing a GreenPAK with built-in power FET. The trade-off there is that this particular part, the 46116, only has 2 analog comparators. So we're going to have a way to, keep an eye on that charging current. For the charging itself, what we're going to adopt is using a pulsed battery charge, whereby the current pulse magnitude stays constant, but we're actually going to vary the duty cycle that the battery actually sees. So in that way, we control the average charging current going through to the battery. And as I promised, the current threshold monitoring, in this case, we're actually going to do a little bit indirectly by detecting when the duty cycle actually falls below a certain threshold. So it's actually a kind of a clever way that, I have to credit Dr. Ramaswamy about this, in doing it that way, and thereby, using as minimal resources as possible in both the GreenPAK as well as externally. And for those of you who might be a little bit concerned about how we're doing the charging, actually there's a number of lithium-ion battery chargers out there that do it exactly in this way. And it's actually very well suited for this battery technology. All right, so let's look at the overall schematic here, what we're looking at. Let me walk you through it here. So in the center of your screen here, you'll see our GreenPAK device. And what our GreenPAK device does is the following. You'll see here that the lithium-ion battery is on the right-hand side. And in the beginning, what we'll do is that if it's deeply discharged, we're going to give it a little bit of trickle charge, all right? And then as we're moving into the bulk charging phase, or that constant current phase, we're basically going to derive or get our current from the main supply. In this case, it's a 5-volt supply, and basically pass it through onto the lithium-ion battery. And by basically controlling the on and off of this pass FET, we can control how much current the lithium-ion battery is actually getting. And on the left-hand side here, you can see a couple of things. They're just indicator LEDs to tell you which actual charging phase you're in at any given time. The way we design it here is that only one light will be on, but it's kind of nice for your application. And I think it kind of really highlights how your GreenPAK, if you want to add these features, or maybe if you don't need it, you want to eliminate it, for example, to move to a smaller and cheaper device, it's all within your capability to do. And a couple of notes about it. For the GreenPAK itself, as I mentioned, you can either use the standalone GreenPAK together with the external FET of your choice, or you can adopt a more integrated approach, which we're doing here by using the 46116. That particular part can push as much as 1 amp through its integrated FET. And a couple of design notes here. So you'll see here that there's a diode here, D2. Well, if you go the external FET route, and that external FET has reverse voltage protection built in, such as is the case with all of Dialog's green FET products, you can actually eliminate this particular diode. Furthermore, if you're charging from a source that already has built-in current limiting, you can actually eliminate the R2 resistor here. The trickle charging is controlled by R1, and in this particular case, we've set it such that it charges at about between 20 to 35 milliamps, and it's great because we can just use one of our built-in GPIOs to do that. It's well within the capabilities of our GreenPAK products. And lastly, on this slide, on the right-hand side, you'll see a RC network here. R3 and C2 basically form a low-pass filter that filters out any particular noise or ripple on the from the PWM waveform. So, I mean, as you can see here, it's actually very little BOM components here, and most of the complexity is actually in the GreenPAK design itself. So, and that's what you want to have in your particular circuit. You don't want to have so many components on your board itself. And here, again, we're going to zoom into what's actually inside the GreenPAK design. Suffice it to say on this slide that the lower left-hand side is your PWM control circuitry, and we're going to step through each and every one of these blocks here. So don't worry if it's about to tick in at once. But that's our PWM controller circuitry. As you can see here, we have some various analog comparators and logic circuitry connected up to indicate when we're in certain modes on the top half here. And if you decide to adopt an external FET for your particular design, we actually offer, well, it's been configured such that you can drive those FETs. And you would only use one of the two, not both of them. Whether it's a logic low or logic high device. So let's jump into it. The first part of the design is really all about the PWM generation. And so what I've done is, for those of you who haven't gone or seen some of the prior material or some of our prior app notes, just talk a little bit about how to generate the PWM signals. So what we're using here is a lookup table to take in inputs for set and reset, and based on what those signals are, our output would either increase or decrease in duty cycle. And you can see here it's kind of configured in such a way. I think the waveform kind of explains it all. Any set signal basically makes the output go high, And any reset signal would basically override that and cause output to go low. All right. And what's important about noting this is that by using these signals and changing the set and reset signals, you can actually either increase or decrease the duty cycle of that output. And this is how we do it. We basically shift the set or the reset signals, just offset it and shift it relative to each other to achieve either a shorter or longer duty cycle. And the way that we did it or the way that Yuhan did it in her application note is she shifted the counter output earlier in time relative to the other one. So on the top half here, you can see here that whereas the first pulse was 80 pulses apart, the subsequent one was just one shorter. And you can see here that it just gets like shorter and shorter and shorter relative to reset. And what that does is that effectively the PWM signal increases in duty cycle. And the opposite is true. If you want the PWM signal to decrease, you would shift the reset signal instead while keeping the set signal fixed. So that, in essence, like decreases your PWM, and that's really what we're doing in this particular circuit. And just to walk you through how it's implemented. So counter 2 and counter 3 generate those aforementioned set and reset signals every 62 clock pulses, right? And what they do is that those particular counters, they feed into a downstream lookup table number 10. It's not shown here, but they feed a downstream lookup table to generate 100 Hertz rectangular waveform. Now, the down-up signals that kind of determine the set and reset is actually derived from monitoring the lithium-ion battery voltage. So as the lithium-ion battery kind of falls in its level, we'll basically increase the charging current or decrease it if it starts reaching its full state. So let's see. I think the only other thing I want to mention here is that the counter 4 is responsible for making updates happen every 2.5 seconds. We kind of chose a frequency that is fast enough to respond to any like overcharging events, but slow enough to make sure that the battery has enough time to kind of settle. So you can obviously change any one of these parameters when you download this design and just start playing around with the parameters. And if you want more detailed information on this, you can look on our application notes on the PWM engine design, either app note 1117 or app note 1122. All right, looking at the charging algorithm. Now, if the battery is in a state where it doesn't have much charge, say it's less than 2.5 volts, the analog comparator number 1 would turn on a signal to signal the start of the trickle phase. And that's where we start driving about 20 to 30 milliamps into the battery. That should be a low enough current, and it's done very deliberately. We actually inject a steady current because if the battery is in a very low charge state, you don't want to be pulsing it with like huge current magnitudes. It might cause some damage or some overheating, for example. So definitely don't, this is why we've chosen like a direct current of very low magnitude. And once the battery voltage reaches about 2.5 volts in our particular design, we've determined that it's ready for a high current bulk charging phase. And that's when the PWM output comes on. And for our particular case, we chose 2.5 volts, but for your design, maybe you determine that it should be lower than that or higher than that. It's so easy to just change the parameters in analog comparator number 1 to do that. So when we're in that bulk charging phase, the PWM duty cycle, you can imagine, begins at closer to 100%. We want it to have a relatively fast and high charging current until the absorbed state is reached. And we ensure that by putting a delay block inserted right before the counter 3. that sets the set pulse at the PWM SR latch lookup table number 10, which is it's shown right here. Yeah. So that pretty much sets the stage for the subsequent charging phase. So what happens when the battery voltage reaches about 4.1 volts, which is usually about the level of most lithium-ion batteries. It's usually around 4 volts or so. But the absorbed state at that point is signaled when the battery voltage crosses the analog comparator number 0 threshold for the first time. So you could set that at 4.1 volts. The OR gate L1 latches on, as you can see here by this feedback connection, to signal that the battery is in absorbed state. And then the AND gate L0 is added so that the analog comparator 0 output is pulled only when a pulse emerges from counter 4, which is kind of chopped off here, but this lower connection goes to counter number 4. In the absorbed state, an AND gate L2, also not shown here, allows the update pulses to go through. And all during this time, during the charging state, the duty cycle is constantly adjusted to maintain the battery voltage between the hysteresis limits of analog comparator number 0. And you can imagine that as the battery charges to its full state, the required duty cycle becomes lower and lower and lower until it finally drops below a predetermined threshold. And in our particular case, we choose something like 10%. So let me walk you through the design for the charge termination logic here. We thought it best to kind of just show it in a picture so you can get a good idea of what we're going for, and then I'll delve into the actual details of that. A quick check on time here. So this is an illustration when that analog comparator 0 is checking to make sure that, okay, charge termination is reached. So the first set pulse comes from counter number 3, and that triggers the L2, our update pulse, to go high. And based on that, following that, actually, lookup table number 0, that pulse gets split into extra pulses. And what that causes is the following. It causes the reset signal to go just prior to the set signal. And whenever that happens, as we explained in the prior illustration, that starts causing the PWM pulse to be shortened in width. So you can see that in the number 3 illustration here. You can see it being shortened as soon as that reset pulse comes up sooner, right? And then, you know, further down the line, I mean, we put in a delay here. The delay is actually very deliberate, but you can see here that eventually there's the delay 5 block, which is responsible for detecting whenever the duty cycle has become low enough. That's how we're going to indirectly sense that it's time to, you know, back off on the charging current because basically the battery is already full, right? So this is what we're aiming for here. And this is how we actually do it. For the charge determination, first of all, you set what your threshold, what you want it to be. In our case, is 10%. And the one thing to note is that the PWM waveform has as many clock pulses as the data field of counter 2 and 3. And based on that, we need to sense when that PWM pulse is shorter than 10% of that particular data field. So to really drive home the point, here's an example in our design case. You can see here that, or see previously that our counter 2 and 3, those data fields were set to 62. So the PWM period is subsequently 62 pulses long. Now we want to sense when the data field for our, let's call it a filter block delay number 5, delay block 5, when it's 10% less than that. So in this case, it's 56 or 6 pulse widths less. And it acts as a filter so that whenever the delayed falling edge appears on its output, that happens when the PWM's low pulse is longer than 56 clock pulses, all right? So lookup table number 2 checks to make sure that analog comparator 0's output is high, latches it into a high state, and that essentially starts to signal that your charge termination is reached. And to restart the entire charging cycle after this, you basically have to power cycle it. That's how we've done it in this particular design. All right. So how do we do? In terms of test results and notes, in the lab, we tested it on an SLG 46533 together with a 3.7 volt lithium ion battery. And based on the schematic values that Dr. Ramaswamy used, he had set analog comparator 0 to an in voltage threshold of 1 volt. The absorption stage kicked in at 4.7 volts, and thereafter it was pretty much maintained between 4.03 and 4.07, which is kind of in the sweet spot for most lithium-ion batteries. The charge current at the start of the absorption stage was about 0.5 amp, and that was really just limited by our 5-volt USB charger. Some design notes to keep in mind. This particular design doesn't test for duty cycle, underflow, or overflow, but you can easily add it. We decided to keep it simple. Our prior design done in app note 1202 actually had that in there. So you can easily add that into this design to do that. Another thing to note is that the low pass filter R3 and C2 prevented any ripples from erroneously triggering faults in our circuit. And you can definitely experiment with these two RC values. And one thing, keep in mind that when you're increasing the value of R3, our GreenPAK analog comparators have an input impedance of about 1 mega ohm and gain error of about 3%. So just keep that in mind when you start increasing that. Now, in wrapping up, I mean, one of the questions you may ask is, what's the advantage of doing it this way, or why would you, as a system designer, want to choose this particular way of implementing your circuit? Well, there's a number of reasons, and in certain cases, CMICs are advantageous over discrete and off-the-shelf fixed function type ICs because when energy harvesting applications come along, the requirements can be relatively unique. Those of you who work with them can, are definitely familiar with this. Or if your design, any design you have has unique requirements, I mean, that's really where these parts shine. So the first advantage is that you can integrate this particular solution, in this case, this was lithium-ion battery, together with any other function you may be doing. For example, you can integrate this lithium-ion charger circuit together with a lot of the supercapacitor monitoring and cell balancing circuit that we presented in the past. So in this way, by integrating all these functions, you reduce your solution footprint, you reduce your total BOM cost. The second thing, hopefully you've gotten the idea from this webinar and our prior ones, is that you can really customize the solution by incorporating these context-specific control mechanisms. So in essence, it gives you a fast custom solution that doesn't require any NRE. Unless you're a really big customer of a particular supplier and can request a custom ASIC, I mean, it's really difficult to come up with a really custom design without going to discrete parts, for example, or paying a lot for off-the-shelf one. Another added advantage is that because you have all of these resources that you're configuring within the GreenPAK product itself, you can be much more power efficient. If you don't want to pull a particular input very often, you don't have to do that. You can kind of turn off the oscillator, not use certain analog comparators. Another thing you can do is utilize our asynchronous state machines to basically only react whenever there's an event that comes along. So in that way, you can achieve a lot lower power consumption, let's say in the nanoamps, whenever you're in an idle state and nothing's happening. And finally, the one thing that you may not realize right away is that with a single integrated IC, I mean, what you have in essence is a fully tested and guaranteed IC solution. If you were to build it discretely, for example, with many components, we've seen as many as 10 or more. But in those cases, I mean, you have so many different parts on your system, and you're going to have to test it as a whole system and run it through qualification and your, reliability tests. In this case, we sell it, from the factory fully guaranteed with a data sheet. So in that sense, it's higher reliability compared to discretes, and overall just less maintenance and cost. And in wrapping up, looking at this design, some possible things that we can look at is experimenting with different PWM frequencies for your particular lithium-ion chemistry. You can definitely add temperature monitoring. We've shown how to do that in many other application notes. And by doing that, one thing you can do is add the ability to vary the charge current and termination threshold depending on the battery temperature, to ensure that you're not charging it too fast and heating up the battery, for example, in which case you'd want to back off, right? And thereby extend your battery life. Another thing about our GreenPAK products is that they all have, or not all, but a number of them have I2C built in. So that allows user control over these parameters like termination threshold or any of the thresholds that determine when you go from one state to the next charging phase. So that's really nice, because then you can adapt it to different lithium-ion chemistries as they are introduced into the market. So if you want to find out more about any of what I've talked about today, definitely visit our website. The primary one for energy harvesting one is on our supercapacitor landing page shown here. But otherwise, our application notes, you can go to that page and kind of just do a tag search for whatever subject you're looking for. So that pretty much concludes our webinar for today. I hope you guys all found it informative. I can take any questions if anyone in the audience has any. So let me just wait for anything to come in. Okay. Yeah, I mean, feel free if you guys have it. There should be like a button there for Q&A. You can just hit that, or also hit the, well, that's the main one actually. So I don't see any questions coming through. All right, well, in a concluding remark then, our Director of Marcom, Charing Nguyen, whom you've all probably registered with, she'll send you out a link with our all of these videos and links to our website. So definitely keep on the lookout for that. And we hope you join us in our subsequent seminars and webinars from Dialog Semiconductor. Thanks, everyone, and catch you later.